This video is about covalent bonds. You should already be able to describe and identify covalent bonds and draw simple Lewis structures to determine their dipole moment. But by the end of this video, we'll review that as well as calculate the heat of formation of a covalent bond. So the question of the video is, are all covalent bonds created equal? Similar to the last time when we did it with ionic. Do all these bonds that break require the same amount of energy? Or if I form a bond, will it release the same amount of energy depending on what elements involved? So first we want to make sure we can draw the Lewis structure to determine what kind of bonds might be breaking and forming. We need to add up all the valence electrons when we start. The example we're going to do is CCl4. Carbon has 4 valence, each chlorine has 7 for a total of 32 electrons. We're going to draw a skeletal structure where the least common element of your example is in the middle and the more common element, like chlorines, there's 4 of them, are around the outside in a somewhat symmetrical shape. We're going to subtract 2 electrons for each bond you just drew that connected the carbon to the chlorine. Since I drew 4 bonds, that's 8 electrons. And that means I need to show 24 more electrons. You draw those 24 electrons as dots around the atoms to make sure that they have octets. Chlorines need 6 more dots because they had 2 in the bond, and then you need an octet or 8 electrons. This should work out perfectly for now because we're going to still be looking at some examples from year 1 where they were a little easier and they're all going to work out perfect. So once you draw your molecule, there's a certain geometry that we talked about last year. Linear geometries mean they're flat planes like CO2 or H2. A bent geometry means it's literally bent up like water, and the reason that they're different, even though they look similar to CO2, is that oxygen has lone pairs or extra electrons on the central atom, and carbon did not. So carbon is straight across, and oxygen has those extra electrons pushing on the bonds. Pyramidal means it's more of a triangular shape. Sometimes we call it triangular pyramidal, like ammonia that you see on the right. And tetrahedral meant it was more like a T-shape, but not at 90 degrees, so it's kind of bent up, and there's no lone pairs on the central atom. So putting that all together, we can see if something is going to be polar or nonpolar. So the polar bonds that we talked about before, by having a difference in their electronegativity, can have either polar or nonpolar molecules. It depends on symmetry. So a polar molecule can have polar bonds because it's asymmetric, or a nonpolar molecule can have nonpolar bonds or polar bonds because of its symmetrical shape. So you're going to either get a polar molecule because it had polar bonds, or you're going to get a nonpolar molecule because either it had polar bonds and they were completely wiped out by symmetry, or they always had nonpolar bonds. So water is polar and like dissolves like. This is the reason why we even really care about this. Polar molecules will dissolve in polar water. Nonpolar molecules will dissolve in nonpolar solvents. And also, we know that these polar things are attracted to electromagnetic fields. So what I think you should do now is try to draw out your diagrams, pause the video, and determine their geometry and polarity, and then check with me. So for O2, it's just a linear object with no dipole moment. CF4 is a tetrahedral with no dipole moment because it's symmetrical. N2 is also linear and nonpolar because they're symmetrical. SF2, which was already drawn for some reason, is polar because there's a sulfur pole and a fluorine pole. The molecule is bent. PF3 is pyramidal. The P is one pole and the F's are the other pole, so this is polar. And SiH4 is tetrahedral. This is not polar because it's completely symmetric. So you're going for symmetry here. Is it symmetry, like if you cut it in half in both the Y, X, and Z direction, will it be the same on both sides? Some more examples. Now that we're in AP, we might draw where the dipole moment is headed with an arrow showing that the more negative side is going towards the arrowhead. So in HCl, chlorine is more electronegative, so you draw like an arrow towards chlorine saying the electrons are migrating that way. And that's why if you look at these diagrams you might see like in a textbook, there's going to be more electrons around the chlorine, so the electron cloud is a little denser around the chloride, so they show it as like a reddish color. In ClCl, there's no pole in electrons, they're sharing equally, so you can see that the density is the same for each one. There's a nice even coating of green. Similarly, CH4 is nonpolar because there's no two sides, so you can see it has a nice symmetry of like blue at the poles. Every single pole is the same. But for SH2, there's a sulfur pole that's more electronegative because so it pulls electrons towards it more of the time than the hydrogens, and that's why you're getting this reddish pull towards the sulfur side. It has more electrons than the blue side. So I always think is the red side is where the electrons are the most commonly found, because red, you think of like red and hot. I don't know, even though blue is more hot. I don't know how you want to think of it, but they're just showing you that there's 2 poles. So now that we know how to draw them, we know that we have to calculate heat of formation of both ionic and covalent. In the last video, we talked about ionic compounds and how we did, its lattice energy. Well, there's no lattice in these. These have completely different shapes. So instead, we have to see how much energy is taken to break and form bonds. And in that case, we should know the following rules, and they're red because you should write them down. That forming bonds is exothermic, and the values need to be negated, because that means releasing energy. And breaking bonds is endothermic, and that means their values should be positive values, because we're going to put energy in to break the bonds. And so when you're doing your heat of formation, all you're doing is looking up these values on a big table, which is found in your textbook, or I'm going to put one up here. And you're just going to add bonds together depending on if they're positive or negative, so summing all the bonds. So this is what it looks like. It's just a big list, and they all look a little different. They're organized different, but the values are pretty much the same. And you can see what kind of patterns we have. They have like a single bonds all on the top, and then have multiple bonds on the bottom. And you can see they're all completely different. So what patterns emerge when we see single versus double or triple bonds is that the single bonds, depending on where you look, might be in the hundreds, maybe as high as 400s place. But the multiple bonds are way, way more. They start at 400s and go up to as many as 1,000 kilojoules per mole to break those bonds. This is all breaking because it's all positive for me in my head. But if I wanted to form them, they would be negated. That's all, right? So we can see that it's much harder to break double and triple bonds than it is to break single bonds. And another question I have here is what patterns emerge when you look at elements in the same group. So like if you were saying something like the NH bond is only 391, but if you look at something like the OH bond, no, same group. So NH bond is 391, so we would look for phosphorus and hydrogen. I don't see that one. How about CCl, CBr, Ci? This is a good one. CF is 485, CCl is 328, CBr is 276, and Ci is 240. As we're going down the halogen group, it looks like it's easier and easier to break those bonds. It might have something to do, something like Coulomb's law, right? Where the electrons are further from each other because the more distance between them, because there's bigger radii for each of those halogens as you go down. So the bond is being easier to break because the protons are not as close to those electron clouds as you had hoped. And you can see that wherever you look. So here's another one, HF, HCl, HBr, HI. Again, it's decreasing its bond energy because the atoms are getting much, much larger, and therefore the other elements, protons, can't help them share electrons as well, right? So now using something like this, you would calculate how much energy was given off by this reaction by first drawing out all your compounds. So CH4 is a tetrahedral molecule. There are 2 chlorines. I would draw it twice just to make sure. You don't have to, but I would probably, or at least put a coefficient of 2 there. Similarly to fluorines, I'd probably draw it twice. A big arrow. And then CF2Cl2 means the carbon's in the center, 2 fluorines on one side and 2 chlorines on the other. Oh, one of those should be a fluorine, sorry. And then 2 HFs and 2 HCls. So on the left are all the bonds I have to break. I have to break every single one of these lines. And on the right, I have to form all of these lines using the previous pictures. So I would look them up. There are 4 CH bonds, and on the previous side, that was 413. There are 2 chlorine bonds, 1, 2. They are each 242 on the previous slide. There are 2 F bonds. They are both 155. On the right side, I'm going to form all these, so they're going to all get negated. Notice I put a negative in front of all the numbers. I just thought it would be easier, but you can negate them all separately if you'd like. So there are 2 that should be ACF bonds. I remember this is a typo here. This should be an F. At 45, there are 2 CCl bonds at 328. There are 2 HF bonds, and there are 2 HCl bonds. And then you just sum this up in your calculator, making sure you use all your parentheses that you need. And I get this value. What this value means is it's exothermic reaction, that this reaction will spontaneously happen for this temperature as long as it's also entropic, which we're going to get to later in the year. It's a more stable compound when it forms because it's exothermic. At this point, you should be able to identify covalent bonds, draw their structures to determine their dipole moment with an arrow, and also calculate the heat of formation of covalent bonds.